Welcome back to the deep dive. Today, we're jumping into something pretty significant in the AI world.
Yeah, we're looking at the abstract reasoning corpus, ARC-AGI.
Oh.
It's arguably one of the most important benchmarks for AI reasoning right now.
Exactly. And our mission today is to unpack a really recent, kind of stunning breakthrough that seriously pushed the state-of-the-art score forward.
And it lands right in the middle of this big paradox we see with modern AI, doesn't it?
It really does. You have these huge language models, right? They can ace the bar exam. They can do incredibly complex physics problems, win math competitions.
Stuff that requires immense knowledge.
Right. But then you give them these, simple visual pattern puzzles, the kind a kid could solve, and they just fall apart. Total failure sometimes. And that just perfectly highlights this core limitation. They're amazing with stuff they've seen or patterns similar to their training data, but generalizing completely new rules. That's the hurdle. They know a lot, but they don't always think flexibly. They're not great abstract reasoners, generally speaking.
And that ability, or inability, to generalize is exactly what ARC-AGI is built to measure. Which brings us to the breakthrough from Jeremy Berman's latest system.
Yeah, this wasn't just a small step. Let's get into the numbers because they really paint the picture.
Okay.
So, on the older ARC benchmark, ARC-V1, still pretty tough. Mind you, this new system hit a new high score, 79.6%, which is impressive on its own. But the real eye-opener was ARC-V2.
Right. ARC-V2 is the much harder version, released early 2025. Before this, the best score anyone had managed was, 25%?
Just 25%. And this new system, it jumped to 29.4%.
That jump, nearly 5 points on the hardest set, is genuinely huge in this context. It signals something fundamental might be changing.
And there's more to it. Efficiency gain is almost as startling.
Oh, absolutely. The program is something like 25 times more efficient cost-wise. It brings the cost per task down to around $8.50.
Compared to
Maybe $200 per task for some of the other top approaches, like early versions of O3 Preview. So way better results, vastly cheaper.
Okay, better, cheaper. How? What's the secret sauce? Because this is where it gets really interesting.
This is the counterintuitive part. They achieve this by swapping out code for plain English.
Wait, really? They were generating Python functions before, right? Deterministic code?
Exactly. Within the same core architecture, this evolutionary test-time compute framework, they just changed what was being evolved. Instead of Python functions, they started evolving natural language instructions.
That feels backwards. You'd think precise code would always beat fuzzy language for defining rules.
You would. And that's why this is such a key insight. The fact that natural language worked better and cheaper here is, well, it's the core of what we need to unpack today.
Okay, before we dive into why English beat Python, let's just solidify what ARC-AGI actually is. What's the test like?
Think of it as basically a visual IQ test for AI. It uses these grids of colored squares.
Like a matrix reasoning test, sort of?
Yeah, exactly. Or a nonverbal IQ test. It's designed specifically to not rely on the massive amounts of text or images the AI has already been trained on. It's about figuring out something new.
So you see a few examples like input grid A transforms into output grid B, input C into output D.
Right, maybe 3 or 4 examples showing a transformation rule. Then you're given a new input grid, and you have to apply that same rule to produce the correct output grid. The key is, you've likely never seen that exact rule before.
And V2 is significantly harder than V1.
Oh, massively. V1 had some tricky ones, but V2, the 2025 set, it requires multi-step, sometimes nested, logical reasoning. It's not just change red squares to blue. It's more like find the largest symmetrical object, identify its primary color, find all squares outside that object matching that color, and rotate them 90 degrees.
Wow, okay, that sounds complex.
It is, and that complexity creates this huge gap between humans and AI. Smart humans can look at a batch of, say, 100 V2 challenges and get 100%.
And the best AIs were stuck at, 16% before this latest jump. Now 29.4%, still a massive difference.
A chasm. Really. And that chasm is why ARC matters so much. It's not testing memory. It's testing the ability to learn genuinely new skills, to generalize way outside the training data. That's why people see it as a key indicator for artificial general intelligence, or AGI potential.
So if this is our best test for AGI-like reasoning, how did Berman's team get that 29.4%? Let's get into this evolutionary natural language method.
Okay. So the foundation was already there from about 10 months prior. Berman's original system used this ETTC architecture evolutionary test time compute.
And that original system used models like Sonnet 3.5.
Yeah, models like that. And its job was to generate Python functions, little snippets of code that, if correct, would perform the grid transformation.
Deterministic testable code. So why did they pivot away from Python for V2? Why didn't that work anymore?
Well, the source material really digs into this. The V2 transformations, like that complex example I gave, they're just messy to express cleanly in code.
So trying to write a Python function for those rules would just be incredibly complex and fragile.
Exactly. You'd end up with these enormous brittle functions full of edge cases. It required a level of nuanced pattern recognition and sort of contextual understanding that just doesn't translate well into rigid code structures.
Okay, so Python was too brittle. They stick with the evolutionary architecture, the ETTC framework, but switch the output. Instead of code, they start generating natural language instructions using Grok 4, primarily.
Correct. But the crucial point is how they evaluated these instructions. You mentioned earlier, isn't language too ambiguous?
Yeah, how do you score an English sentence for correctness in transforming a grid? Code runs or doesn't, roughly speaking. Language is fuzzy.
That's the clever part of the V2 loop. The language isn't the end product itself, it's the recipe for an action.
Okay, walk me through that loop, stage by stage. Right. So
Yeah.
first is generation. Grok 4 generates a set of plain English instructions, like step 1, find the blue squares, step 2, move them down by one row. Just straightforward instructions, then what?
Then evaluation. This is key. A separate sub-agent model takes that English instruction and actually tries to perform it on the example input grids. It manipulates the grid based on the text.
So the language guides an action. It's not just assessed on its own.
Precisely. Language in, action out. Then comes scoring. The system compares the grid manipulated by the subagent to the actual correct output grid, the ground truth.
And it gets a score based on how close it is.
Yeah. And importantly, it's not just pass-fail. It can get partial credit based on, say, the percentage of correctly colored cells. This allows instructions that are partially right to still be valuable.
Okay, that makes sense. So even a flawed instruction might have some good ideas in it.
Exactly. And that leads to the final stage, evolution. The instructions that got the highest fitness scores, the ones that resulted in the most accurate grid transformations, they become the parents. Natural selection for instructions. Basically, yeah. These successful instructions are then used to generate the next generation of instructions, hopefully refining the solution. It's evolution operating on meaning and process, not just code syntax.
And this refinement, the evolution part, that's where these different strategies come in. Individual and pooled revisions.
That's right. Those are the two main ways the system tries to improve the instructions generation by generation.
Okay, tell me about individual revisions.
Think of it like targeted feedback. The system takes one specific instruction that didn't quite work. It shows the model, the instruction, the incorrect grid it produced, the correct grid it should have produced.
And crucially, it highlights the difference. Yes, often with a little text-based diff showing exactly which cells are wrong. The prompt is essentially, here's your instruction, here's where it failed, fix the instruction. It's very focused editing. Okay, that sounds logical. What about pooled revisions? That sounds more complex.
It is more ambitious. Here, the system takes multiple high-scoring instructions, say, the top 3 parent instructions from the previous round, and puts them all into the same context for the LLM.
And the goal is, the prompt is basically, look at these 3 instructions. They all got parts of it right. Can you synthesize their strengths? Combine the good ideas from all of them into one new, hopefully better instruction. It's trying to breed a superior solution from multiple good parents. Conceptually, that sounds like the smarter approach. Combining the best bits should yield better results, right?
You'd think so. But here's where we bump into another one of those fascinating counterintuitive limits of current LLMs. Pooled revisions weren't always better.
Why not? Well, there's a practical issue first. Token limits. You can only cram so many lengthy instructions into the model's context window before it just, runs out of face or takes forever. Okay, the plumbing problem. But there's more to it.
Yeah, the source material points to something more fundamental, degraded reasoning. It seems that, much like humans, if you overload the LLM with too many different inputs or too much complex context at once, it gets confused, loses focus.
Something like that. The quality of the synthesized instruction could actually go down. The model struggles to effectively integrate all the ideas, and the resulting instruction might perform worse than the individual parent instructions it was based on.
So more context isn't always better for LLM reasoning. It can actually hurt performance.
It seems so. It suggests it's not just about compute limits, but maybe a limit in the model's ability to maintain focus and synthesize complex information without getting muddled, kind of like cognitive overload in humans.
So how did they structure the final system then, knowing this? Did they use both strategies? Yes. They ended up with a multi-stage, sort of resource-aware design. It tries to balance broad exploration with focused refinement.
How does that flow?
They start by generating maybe 30 initial candidate instructions using Grok 4. Just a broad first pass.
Okay, lots of shots on goal.
Right. Then they take the top 5 performing instructions from that batch. These 5 get put through the individual revision process, so that adds 5 new, hopefully improved, candidates.
So focused editing on the best initial ideas, what if those still don't solve it?
Then they take those same top 5, or maybe the best performers after individual revision, and feed them into a pooled revision prompt, trying that synthesis approach as a next step. This potentially adds another 5 candidates.
So maximum of around 40 attempts per task. 30 initial plus 5 individual plus 5 pooled.
Something like that, yeah. It's a layered approach. Start broad, then refine individually, then try to synthesize. It allows them to explore possibilities without the potentially massive cost of, say, running cooled revisions on everything from the start.
And this careful, staged process is what got them to that 29.4% score more efficiently.
That seems to be the case. It's clever engineering around the model's capabilities and limitations.
Okay, but even with this success, 29.4% means it's still failing on over 70% of these really hard V2 tasks?
Absolutely. And the way it fails is perhaps even more revealing than the successes. This leads us to this idea of dead reasoning zones.
Right. Let's connect this back to AGI. You mentioned Francois Chollet's definition earlier.
Yeah, Chollet defines intelligence, or AGI, largely by the ability to efficiently acquire new skills far outside the training data. And the way LLMs often fail ARC tasks seems to violate that efficiency principle pretty spectacularly.
They don't just get the answer wrong, they get it wrong in ways that seem illogical.
Deeply illogical sometimes. Berman mentions seeing thousands of examples, traces where a model will think for ages, maybe 20 minutes of computation,
Okay.
only to confidently declare that an object in the grid is perfectly symmetrical when, visually, it's obviously glaringly not symmetrical.
And it can't see the error, even if prompted.
That's the really weird part. Even when you point out the asymmetry, the model seems unable to internally recognize or correct the logical flaw. It's like a blind spot, but for logic. These are the dead reasoning zones.
So pockets within the model's neural network where fundamental logical operations just don't compute correctly.
That's the idea. It's not that it lacks knowledge, it's that the reasoning mechanism itself seems broken or inconsistent in specific contexts.
It's like someone who understands physics perfectly but suddenly can't grasp gravity if the object is painted green. The logic breaks down under arbitrary conditions.
That's a good analogy. It's incredibly fragmented. Whereas humans, well, we might not know quantum physics, but our basic logic is usually consistent.
Right. A human who's logical about economics is generally logical when they try to learn programming or solve a puzzle. The reasoning transfers.
Exactly. Humans might have dead knowledge zones, things
Yeah.
we just haven't learned yet, but we don't typically have dead reasoning zones where basic logic like symmetry or object permanence just disappears.
So what causes these dead zones in LLMs? There's this theory about a fused circuit problem.
Yeah, this is getting into the theoretical underpinnings. The idea is that current LLMs, during their massive training, don't learn logic as a pure universal skill. Instead, they learn domain-specific reasoning patterns. They learn math logic, which works well for math problems, code logic for programming, language logic for text. And these reasoning patterns get kind of fused or entangled with the specific neural circuits handling that domain.
So they're overfitting the reasoning to the domain. They learn how to sound logical within, say, a Python context, but they haven't mastered the underlying universal principles of logic itself.
That seems to be the leading hypothesis. They mimic logical reasoning within familiar patterns, but when faced with a truly novel abstract task like ARC, which doesn't fit neatly into a learned domain, the underlying inconsistencies show up.
Okay, so if that's the problem, what's the solution? How do you fix these dead zones and get truly general, consistent reasoning?
This is where Berman's thinking, and others, seems to be evolving. The previous approach was mostly induction training models to predict the next word.
Which teaches them to generate text that sounds plausible based on the patterns they've seen.
Right. It generates text that is statistically likely, that sounds correct, but it doesn't necessarily enforce actual logical correctness or consistency.
So the proposed path forward involves reinforcement learning.
Specifically, reinforcement learning applied over the model's chain of thought process. The idea is to reward the model not just for the final answer, but for the logical validity of its reasoning steps.
Ah, so you're not just rewarding sounds right, you're rewarding is right, and here's the valid logical path to prove it.
Exactly. RL can, in theory, force the model's internal weights, even the pre-trained ones, to become more logically consistent. It teaches the model what sequence of thoughts, what internal words or steps lead to a verifiably correct outcome.
You could argue the evolutionary system we discussed is already doing a form of this, right? The instruction is the thought. The grid manipulation is the action. The fitness score is the reward.
It definitely is. It's a form of trial and error learning focused on the outcome. Applying RL more directly to the internal reasoning trace, the chain of thought, could be even more powerful in forcing that consistency.
So it's a subtle shift in perspective. Maybe the goal isn't just making models that can generalize outside their training data.
Perhaps not entirely.
Yeah.
Maybe the goal is to bring that pure skill of universal logical deduction, the kind humans have, fully inside the model's capabilities, making it consistent across all tasks within its potential scope.
Get the core reasoning engine right, make it universally reliable, and then it can apply that engine to any problem it encounters.
That's the hope. AGI isn't necessarily about escaping the training distribution, but about having a perfectly consistent logical core within it.
Okay, so let's wrap this up. What are the big takeaways from this deep dive into ARC and the new state of the art?
Well, the most immediate and maybe surprising takeaway is the power of natural language in this context. For these really abstract, generalization-heavy tasks, evolving English instructions actually beat evolving deterministic code.
Which tells us something profound about LLMs, right? Their strength might not be just outputting code, but articulating complex, high-level plans or transformations that are just too awkward for rigid code.
Exactly. They can capture nuance and relational concepts in language that are hard to pin down algorithmically.
And this connects to that final, really provocative thought from the source material. This idea that asking these truly novel questions, the ones outside the training distribution like ARC
It's
does.
almost like launching an adversarial attack on the model. It probes the weaknesses, the inconsistencies.
Right. So if this evolutionary process, constantly generating instructions, testing them, and refining based on errors, if that process is essentially a continuous internal adversarial attack finding and fixing logic gaps.
Then, does that imply the path to AGI? To truly general and consistent reasoning is essentially a process of relentless self-attack, constantly seeking out and penalizing every dead reasoning zone, every logical inconsistency, until the underlying reasoning circuits become universally robust.
AGI, through continuous automated debugging of logic itself, that really flips the script on how we think about training these models.
It does. Less about just feeding data, more about forging consistency through rigorous testing and correction.
A fascinating place to leave it. Thanks for walking us through all that.
My pleasure. Really interesting developments.
Absolutely. We'll catch you on the next deep dive.